Hello and welcome back. Today I want to talk about dipole antennas and look at the exact dimension at which they are resonant. Resonance being defined as the frequency at which the antenna shows purely resistive behaviors without any reactive components. I will be looking at both the simulation prediction as well as try to build and measure some practical antennas. So if you're curious, then keep watching. Now, as some of you correctly pointed out, I made a bit of a mistake in a previous video, when I said that the theoretical half-wave dipole is resonant and has a purely resistive impedance of 73 ohms. I was wrong. The theoretical infinitely thin dipole has a complex impedance of 73 plus 42.5 J ohms. And this antenna does become resonant when it is about 0.49 wavelengths long, and then it has an impedance of 70 plus 0 J ohms. Now, theoretical infinitely thin antennas are interesting, but not something you will be building anytime soon. So let's start looking at practical dipole antennas. As before, I will be simulating antennas using the MMANA GAL software, and for the sake of easy numbers, I will start with a 1 meter long dipole, so it's plus minus 0.5 meters. And based on its length, this structure is a half wavelength at 149.89 MHz. But as already predicted by the theoretical dipole, the resonance frequency will be lower somewhere. Now, one key factor other than the antenna length will be the antenna diameter or, well, radius. So in general, a larger diameter gives a wider bandwidth, but it will also have an impact on the resonance point. To get a better idea of how this parameter will impact the antenna behavior, I already simulated this 1 meter long antenna at multiple thicknesses, and to start things off, using a lossless material in free space, so just to make things as simple as possible. So I summarized all of the values in this table, and while the 4 thicknesses I simulated was an 0.00001 radius antenna, so this would be the closest to the ideal infinitely thin antenna, then an 0.1 mm, 1 mm and 10 mm thick antennas. And well, for all of these thicknesses, I summarized the complex impedance and the exact absolute impedance and finally the resonance frequency. So what does all of this data tell us? Well, first of all, the resonance frequency is thickness dependent. So we start off with around 147.8 MHz with the very thin antenna, and then slowly move down to about 139.9 MHz for the thickest antenna. Next, to get a better view of the bandwidth of the antennas, I summarized all of the points in this chart, where we can see how the impedance varies with frequency for the various thicknesses. So our thinnest antenna, the blue one, has the smallest bandwidth. This bell curve is the narrowest, and then the next antenna, the orange one, 0.1 mm, already has a much wider opening. And well, for the other thicknesses, it's not really obvious, because the frequency interval at which I looked is too small. But anyway, as the thickness increases, so does the bandwidth. And well, another thing you can notice is that the resonance point moves slowly to the left. So we have our direct length conversion frequency at around 149.89 MHz, and then with the actual simulated structures, we can see that frequency decreases as thickness increases. Now, the other important consideration when talking about practical antennas will be the loss resistance. So not just the radiation resistance you get with an ideal material, but the loss resistance that you get with real materials. So this is material dependent, we have multiple materials to play around with, and it's also thickness dependent. So again, I ran the simulation for the multiple thicknesses with multiple materials. And if we look at this data, what I have here is a simulation for the 3 more realistic thicknesses with 4 materials, so the ideal one, copper wire, aluminum wire and iron pipe, and I summarized the resistance that the simulation gave us. So the loss resistance in all of these cases will be the ideal radiation resistance minus whatever value we got. So the difference between these will be our loss resistance. Or in other words, the larger this resistance becomes, the more lossy the antenna is. So if we look through the values, well, the resonance frequency didn't really move, based on the material, but what did change was this resistance. And while at large thicknesses, it's not really obvious. So with our 20mm diameter antenna, the resistance is more or less the same whether we're talking about the ideal material or copper or aluminum. But if we move to smaller thicknesses, then the differences start to become a bit more obvious. So to minimize the losses, you will want large diameters and a well-conducting material. So why isn't the resonant dipole antenna exactly a half wavelength long? Or why should it even be in the first place? Well, the general theory around the half wavelength point is that at this specific dimension, the wave traveling through each quarter wave section of the antenna will bounce back from the end and be in exact phase opposition with the incoming wave. There will be a half wavelength delay, or 180 degrees. This will cancel out any reactive elements, and the antenna should have only radiation and loss resistance. In typical explanations about dipoles, especially when highlighting the current and voltage distribution along the antenna, you will see that this current and voltage abruptly stops at the edges of the antenna. So there's a peak current in the middle of the antenna and a peak voltage at the edges. The explanation I found regarding why the half wavelength antenna isn't exactly half wavelength long has to do with the fringing fields around the edges of the antenna. So because of the strong electric fields at the edges, the fields around the antenna don't abruptly stop at the end, but rather they fringe outwards a bit, thus increasing the inductance of the antenna and lengthening its effective length. So the wave that travels through the dipole does not limit itself to the physical length, but rather to the effective length given by these fringing fields, which are antenna diameter dependent. So it's perfectly normal for the antenna to not be exactly half wave long, but rather you get your resonance when the antenna is slightly smaller. Next, it's time to verify these claims and principles with some experiments. For that, I will be using a light VNA to measure a 35 cm long dipole's impedance, an antenna that could be used in the 70 cm ham band. But before starting that, it's important to remember that the dipole is a balanced load, and the VNA has an unbalanced input. To make a correct measurement, we need some sort of adapting circuitry in between the two, a balun. So today I will be using a 1:1 commercial balun, which is rated for a frequency interval of 5 MHz to 1 GHz, and I mounted this on a small adapter board in which one side is an SMA connector and the other is a connector into which I can plug my antennas in. Now, to perform the calibration, open circuit and short circuit is not that difficult, but to perform the load calibration, so the 50 ohm, to have a resistive as possible component, I took a 50 ohm SMD resistor and soldered it to a large value through-hole resistor. So this will be inserted to perform the load calibration. The main reason for calibrating through the adapter is to try to compensate for any non-ideal behaviors brought on by the balun board. So once the calibration is done, it's time to verify the impact of wire diameter on resonance frequency. For that I prepared two antennas, one with a 1.5 mm diameter wire and the other with an 0.7 mm diameter wire. So first off, we have the thicker antenna, which is about 35 centimeters long, and if we run our measurement and try to put the antenna as far away as possible from any impacting structure, and we just pause the measurement. So if we scroll through the values a bit, we can see that we are achieving a almost resonant point, so the reactive component is milliohms at 400 and almost 7 MHz, where our resistive component is 72 ohms and the impedance is, well, again 72. So this is not very far from the simulated value of 407 MHz. So next, I mounted the thin wire. Again, the length is more or less 35 centimeters. If we rerun the measurement and we look through the points a bit, well, resonance seems to be achieved at a lower frequency, although it should be a bit higher, at around 404 MHz, And again, we're getting similar impedance values, 73.6. Now, even though the exact resonance frequencies are not as expected from the simulation, this most likely has to do with the exact physical dimensions of the antennas that I've built. But what can be noticed though from the two measurements is that the bandwidth does indeed change. So when we look at both of these measurements, the thinner wire has a narrower bandwidth compared to the thick wire antenna. Now, the resonance frequency of the antenna will be impacted by its length and diameter. But one more thing to keep in mind is that the wave speed through the conductor is impacted by the environment around the conductor. So for simplicity, air is usually considered to behave like a vacuum, but if there's something else around the antenna, like a PCB or some sort of insulation, this will also affect the resonance frequency, since the waves traveling through the antenna will be doing so at a slower rate. To highlight this effect, I prepared another 35 cm dipole with the same 1.5 mm wire that we've used previously, but this time I left the wire insulation on. So this is some electrical wire. And if we measure this antenna, we can notice that the resonant frequency has been pushed lower, so it's around 380 MHz this time. This is due to the insulation on the wire, which makes the wave travel slower through it, but the bandwidth of the antenna did not change all that much. So the two measurements are very comparable. So this is an important thing to keep in mind with practical antennas. The exact environment around them will have an impact on their behavior. Now, making thicker and thicker dipoles to expand the bandwidth is not always practical. A thicker and thicker wire or pipe will be heavier to the point where the antenna cannot even support itself. To go around this problem, the antenna can be made from wire meshes or plates with different geometric shapes. You have your cage dipole, biconical, butterfly, bow tie, and all sorts of other antennas. By doing this, the antenna will behave as if it's thicker, but it will be built with a limited amount of material. Now, just as a basic example, I made a simple bow tie antenna, and if we measure its impedance and we look through the graph a bit, we can see that the resonance frequency was pushed way down, so this is about 298 MHz, again for the same length antenna, 35 cm, and we can also notice that the bandwidth has also increased. So when building different shapes and types of antennas, again the resonance frequency and bandwidth will highly depend on the exact geometry, not just the overall length. In the end, antenna building can be a fun activity, but the end result may not be exactly as expected. It's common practice to build antennas longer than they need to be, and then just cut bits off the end until the exact resonance point or behavior is achieved. Basic calculations will help you get close to the desired structure dimensions, but it's always easier to perform a simulation. And even then, the practical result may end up being different. The antenna is not just impacted by its own construction, but also by the environment around it, something that is not always possible to model accurately. So, in general, some amount of fine-tuning will always be necessary. And with that said, hope you got some useful information after this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be updated on all my latest videos, and see you next time. Bye bye.